All right, everybody, this is Jim Grossnickle, UW physicist. I don't know if you want to continue your introduction there from that.
Yeah, my name is Jim Grossnickle. I'm a plasma physics scientist at the University of Washington. We're kind of off-campus facility in Redmond called the Redmond Plasma Physics Laboratory, where we work on fusion energy. I'll try to keep this talk pretty simple. I don't know how you guys are probably, some of you guys are probably pretty familiar with fusion and what it's all about, and some of you may not be. Like there's a few talks that have been done on fusion here before, so this is a quick shot of our machine when it was in its clean room when we were constructing it. So, first I want to acknowledge a few people that I work with and some others that gave me some information and helped with the presentation. Dr. Alan Hoffman, who's our director at our lab, and Dr. Yang Guo, who's our principal scientist. And then just as a general fusion energy plasma physics book, book by Friedberg is a very new one, and it's got a lot of good information on even up-to-date research. And then the U.S. Department of Energy also has just more information on energy than you can possibly imagine on their website. My outline will be just to talk briefly about fusion and what it is, and then I'll give a quick overview of the status of some present research, and then go into what we're doing at the University of Washington, which is what I'm obviously most familiar with. And afterwards, if you guys want to come by, we're going to give a tour of the lab for anyone who's interested. So presently in the United States, coal is our #1 source of producing electricity. It's over 50%. Nuclear is second at 20%, and then you can see oil, hydro, gas meaning natural gas turbines, and then other includes wind and solar and geothermal and biodiesel and things like that are all relatively small sources of electricity. The United States actually is the world's largest producer of nuclear energy. Not many people know that. Everybody thinks France is because they're 80 to 90% nuclear in their electricity, but we currently operate about 104 nuclear plants and produce the most power. We also consume the most power.
Your mic isn't headed in.
Oh.
When you turn your head, you can't have it.
Get a little closer, maybe.
We'll just hold it.
All right. So, sort of the impetus for this talk is to get people excited about fusion and why we need it. Presently, our worldwide fuel supply is for fossil fuels and is dwindling. You know, there's about 1,000 years of coal. The United States is like the Saudi Arabia of coal. We have pretty much the whole country almost is just covered with it. So there's a long supply of coal, but there's obvious problems with burning it. Worldwide, depending on who you talk to, there's less than 100 years supply of oil. Same with natural gas, and even just burning uranium, if you don't use breeder reactors, is only about 100 years supply of uranium for doing fission. With the breeder, you can push that up to about 20,000 years. Which one?
The breeder.
The breeder. This is it's a fission reactor that captures the neutrons and makes plutonium and then burns the plutonium. So you basically can burn your 238 uranium, which is the 98% of the uranium that's naturally occurring. Presently, you burn 235, which is the 2%-ish isotope. So there's not very much of it compared to the 238. And then with DT fusion, which is deuterium and tritium, we also, which is also the easiest form of fusion to do, we have about a 20,000 year supply, and that's chiefly due to a limit in creating tritium, which is not a naturally occurring element. It's got to be bred also, usually in a lithium blanket. With DD fusion, which is a more difficult reactor to build, there's about a 2 billion year supply because you can just burn deuterium out of the oceans. So clearly, if we want to have electricity much longer than a few hundred years, we need to go with at least breeding fission or fusion. So nuclear reactions are orders and orders of magnitude more energetic than a standard chemical reaction. Chemical reaction, such as burning gasoline, produces about 97 electron volts, which is a unit of energy per reaction, where you can see a fission reaction produces over 200 million electron volts, so several orders of magnitude higher. And the fusion reactions are all also in the million electron volt range, which clearly shows that there's a lot more bang for your buck in a nuclear reaction than there is in a chemical reaction. So, what is fusion? Well, it's the process that powers the sun, obviously. Protons in the sun are burned under enormous gravitational pressure, and the sun will produce all the way up to iron before it runs out of fuel. In a sense, though, we've been using fusion on this planet ever since it was born. It fuels the wind. Obviously, you get solar power from the sun. Fuels the weather, so even hydropower is derived in some sense from fusion energy. And even, I guess you could say, fossil fuels, if you believe that fossil fuels are created from dead dinosaurs or plants. The plants had to get their energy from the sun as well, so everything sort of is fusion in that sense. The environmental advantages of fusion, obviously, are that there are no emissions, CO2 or otherwise, and currently right now CO2 and greenhouse gases are a big issue with politicians and environmentalists and other people. So the advantages of nuclear in general, fusion and fission, are that there's no CO2. And depending on the fuel cycle you use, there's no radioactive waste with fusion either. A fusion power plant takes up much less space than a wind farm or a solar facility. Also, it wouldn't look as ugly as some of the wind farms out there. There's no pollution that's produced. So, like photovoltaic cells are made out of silicon, and there's some pollution issues with making silicon wafers. And around here, there's a lot of people who are concerned with salmon and fish, so you don't have to create dams to block up rivers and kill fish.
So what's not to love about it?
It's really hard to do. Here's a simple chart showing the mass of the nucleon, hydrogen being the smallest, and uranium up here on the high side. You can see this is basically a chart showing the amount of energy that's available with the reaction. So with hydrogen, if you put two hydrogens together, you've got a lot of energy here available to fuse atoms together until you get down to iron. And with uranium, there's a lot of energy available here to fission atoms down until you get to iron. I'm always going to remove this bullet because it's not entirely a true statement. Fusion reactors could be a proliferation threat if used improperly. There is little or no radioactive waste, whereas there is with fission. There's no meltdown threat. With fission, a lot of people are afraid of a runaway reaction similar to Chernobyl, which melts down the reactor and kills everybody around. But with fusion, that is not possible. Once you take away the input power, the reaction stops. It's kind of like burning wet wood. You can keep a torch on it, and it'll burn, and you'll get more energy out than you're putting in. But as soon as you take that torch off to stop burning the wood, then the burning stops as well. So it's not something that can run away and cause problems that way. And again, whereas with a breeder reactor, you get about 20,000 years, or with non-breeders, only about 100 years of fuel. DD fusion will last somewhere around about 2 billion years. Some common fusion reactions. The simplest one to initiate, and this is the one that's used in magnetic research now, is going to be used in magnetic research, is the DT reaction. It releases a lot of energy. Unfortunately, a lot of that energy is in a very high energy neutron. High energy neutrons tend to do things like make stainless steel radioactive, and so that's not necessarily a good thing.
Unless you're looking for radioactive stainless steel.
The most abundant fuel is that obviously a deuterium-deuterium reaction, which is also produces neutrons, but at a much lower energy level, and it produces some tritium and a proton, and obviously you get a some deuterium-tritium reaction with that as well. Almost working better. So this would be the ideal reaction for near 2 billion years fuel cycle. Some advanced fuel reactions that don't produce neutrons, and this is one of the reactions that my group would like to do in the distant future, is the deuterium helium-3, which produces helium and protons and a lot of energy. And then there are also people, particularly in the electrostatic fusion community, who want to burn p-boron-11, which is the ultimate, I guess, aneutronic fuel, because it doesn't produce any neutrons at all. Yes?
The 2 billion year thing, does that include all of this breeding, so you could go the deuterium down to the helium reaction, down to the barium reaction? Or does that just include the initial?
That's just burning deuterium.
Okay.
And obviously, when you're burning the DD, you get some helium-3, so you get some of this reaction. You also get some tritium, so you get some of this reaction in it as well.
Right.
But deuterium is a relatively abundant element. It's in seawater. So
This is just the terrestrial sources of deuterium.
Just terrestrial sources.
Not
And
the lunar sources or anything
right.
like that.
So that's a good question. Tritium is not naturally occurring, so you do have to breed that. And typically that would be done with lithium. You'd use this high-energy neutron to bang into some lithium. It would make some more tritium, and you essentially have a fusion breeder reactor. Helium-3 is also not naturally occurring, but it is the end product of tritium's radioactive cycle. So if you make tritium, you can make helium-3, but helium-3 is exceptionally abundant on the moon because the sun produces a lot of it and the moon captures it. One of the benefits of not having a magnetic field up there, I guess. So presently there are several different kinds of fusion energy being researched in the world today. The main one is magnetic confinement. There's also inertial confinement, which is often done with lasers, and then electrostatic confinement, which I don't really know that much about, to be quite honest. Magnetic and inertial confinement take up the lion's share of research dollars. As far as commercial reactor research goes, it's mostly magnetic. Inertial confinement tends to be more bomb physics than it does actually trying to make a reactor, because they tend to be very short pulses and long time scales in between shots. Magnetic confinement is also closest to producing a test reactor. There's an international test reactor that is being built supposedly sometime this year over in France. It's called ITER. I'll talk about that a little later in the talk. So, how do we do magnetic fusion? Tokamaks are the most widely researched and the most advanced of the fusion devices. They've been being researched for on about 50 or 60 years now, 50 years now. And they're at the point where they're going to build a test reactor to show that it is actually feasible to move on to commercial reactors. Stellarator is another concept that gets a lot of attention. There's a picture of the W7X Stellarator in Germany here, and it's a toroidal device like a Tokamak, but it is able to run at steady state. So you basically just turn it on and it runs current through these coils and run your plasma that way. The odd geometry has to do with making sure the magnetic field lines are always giving you stability. So stellarators have really come a long way in the last probably 10 years with the advent of being able to do super high-resolution magnetic calculations on computers. Before, people had to do this stuff by hand, and it was obviously would be very difficult to determine what the magnetic geometry of this coil had to be in order to get the right plasma. But you can see the complexity of even a device like this. Building these coils is certainly not easy. Designing them is certainly not easy. And then, there's a lot of hardware inside. Alternate
forms of research like the Tokamak or the field reverse configuration that we work on at the University of Washington are not as well advanced. They've only been really seriously considered for the last maybe 20 years and have not been seriously considered monetarily. But they're much simpler geometry. Our device is actually just linear. It's a simple solenoid, basically. Actually, our device is very close to a theta pinch. So a theta pinch is you run current through a solenoid, and you make a magnetic field, and plasma sticks to the magnetic field, and when you crank up the current, you crank up the magnetic field, and it crushes it down and ideally fuses the atoms. However, ions and electrons are free to move along magnetic field lines. So when you squeeze really hard on these here, they just want to move out the ends. So you'd have to have a device many miles long in order to produce any energy with a theta pinch. So what the Tokamak guys did is they just twisted that into a torus. So you just have these things running around in a circle. Problem with that is once you turn your magnetic fields into a circle, the pressure of the magnetic field on the outside of the torus is less than on the inside, and the plasma just wants to move out to the lower magnetic pressure. So magnetically, it's not a stable configuration for making plasma, so you have to add many more coils. Presently, there are some. The jet tokamak in Europe is the largest and most accessible tokamak in the world. We have one of our scientists actually worked there before coming to work for us. I'll have a picture of that here in a moment. ITER, which is being built now, is the International Thermonuclear Engineering Reactor. It's going to be a very large tokamak, and it's supposed to produce more energy than it consumes. There's several large tokamaks also operating in the U.S. that are research tokamaks. D3D is probably one of the most prominent ones in General Atomics. At least it's one that I've done some work on. And East is a new tokamak that's being constructed in China, and I believe it might be the only superconducting toroidal tokamak that'll be in operation. There may be one in Japan, but I'm not sure. So here's a photo of the jet tokamak, and this is the inside of it. On this side, you can see the plasma during a discharge. And one of the main things to note is the amount of complexity in the interior of this device. Each one of these little plates has to be able to be remotely serviced. Every part in here is actually able to be remotely serviced by robotic arms, because after running deuterium and tritium reactions, it is slightly hot.
And this is many meters high, right?
This is about, let's see, 2.5 meters across, about 2 meters high. So this is a large device. And the engineering in these things is amazing, but also exceptionally complicated. There's very few people who actually can understand and design something like this. This is a cartoon of the ITER device. This will be the international reactor. Cost somewhere in the order of $20 billion over the next 10 years or so. And you can see the 2 meter tall man here. So that gives you an idea of how big this is. And this would be approximately the size of a working reactor should a tokamak become a fusion reactor. It actually may have to be slightly bigger even. But again, you can see the sheer size of this thing. And the other issue that these have is you have to have blankets protecting your device from neutrons. So you have to have blanket material inside here protecting everything. You have to have blanket material outside the vessel protecting everything. Your magnets, particularly superconductors, don't really like getting hit by neutrons. So there's a huge material science issue and engineering issue with designing magnets that can withstand neutron fluxes that a fusion device will produce. So a lot of what ITER is going to be focused on is materials development and things of that nature. So tokamaks have some advantages and some disadvantages. The advantages obviously are they're the most researched concept, and they're pretty close to being able to show that they can become a reactor. The physics looks good. ITER will most likely work, but they're huge. A gigawatt reactor is, a plant would need to be in the just the reactor itself would have to be in the radius of 10 meters or so, and the whole building may be the size of Safeco Field or something like that. So they're not small by any stretch of the imagination. The other thing that tokamaks can't do is burn advanced fuels. In order to burn fuels other than deuterium and tritium, the aneutronic fuels, you have to have an extremely large magnetic field with the tokamak. I will get into that a little bit later. And the engineering needed to build them is, like I said, very impressive, but also it's a nightmare. So at the University of Washington, we're looking into more of what would be a good approach from an engineering standpoint. Assuming we can get the physics, how would you do it if you were just looking at it from engineering? And what we have is a concept we've been working on for many years here. It's simple and linear, called the field reverse configuration. And it's probably the simplest reactor geometry you could make. You keep in mind that the picture of ITER I showed you a while back, and here's a conceptual design of what our reactor might look like with our 2-meter man. The confinement coils are just, again, simple solenoid coils. The whole thing is simply connected, and it also has what's called a natural diverter, meaning that there are open field lines on the outside of the part of the plasma that carry helium, alpha particles, out the ends, and that can be very useful for space flight or direct energy conversion. So you could conceivably just take your alpha particles that are coming out and directly convert that to electricity rather than having to go through a steam cycle or something of that nature. So like I said, the FRC geometry is very simple. We have a simple solenoidal coil that reverses the field. And the process of reversing the field is something we've studied at great length at the University of Washington. It's a flux conserving coil, so we put a magnetic field in here. The plasma itself reverses the magnetic field, and I'll get into a little bit of that in a few slides here, and creates basically like a football-shaped plasma, where the field lines on the outside are able to compress the plasma up against the coils. One parameter that I'll talk about briefly is beta, and that is the ratio of the plasma pressure, the density and temperature of the plasma, to the magnetic pressure. This is an important parameter because it determines how much magnetic field you need to confine a plasma. Tokamaks typically have about a 5% plasma pressure to magnetic pressure, which is why they cannot burn advanced fuels. In order to burn, say, D-helium-3, with a tokamak you might need 30 Tesla or so. 30 Tesla is a lot more than any coil of any reasonable size other than maybe the size of a finger can generate. Whereas in FRC, the magnetic pressure is about equal to the plasma pressure, so there's a chance of burning advanced fuels at much, much lower magnetic fields. And the reason for that, a lot of that is because, if you'll recall, plasmas rotate around magnetic field lines, orbit around them, so to speak, and when they do that, they give off energy. Any object that's accelerating gives off energy. And the higher your magnetic field, the faster these go, the more energy they radiate. So with a device like an FRC, where there's a very low magnetic field, you don't use as much of your energy in your cyclotron radiation with the right word, but anyhow. This allows us to burn advanced fuels. It also means that fusion conditions, the coil designs are much more simple. So there are some definite advantages to the FRC. It's the simplest possible geometry. It's cylindrical, and engineering is very simple. The high beta allows for low field confinement magnets. It's got a natural diverter, which gives you a chance to generate electricity with direct drive, and it gives you that advanced fuel potential. Reaction ions, like in Tokamaks and other fusion devices, would provide much of the current drive. The other thing that's nice about this geometry is it's a very natural geometry for space propulsion. Or if you want to take your reactor out into space, get someplace, and then put it down and use it to make energy, you can do both. There are some problems. The physics is not as well understood as it is in a tokamak, and it's different from tokamak physics. Stability of the magnetic configuration has always been a concern because it only has a toroidal, or it doesn't have a stabilizing magnetic field like a tokamak does. There is a mode that if you have a magnet in a magnetic field that's opposite the direction of the field, north-south, going the wrong way, it wants to flip over. Well, it's sort of what an FRC is. It's kind of a thing that wants to flip over in its field. We have not ever seen anything like that happen in our research, but it's theoretically it's possible. All the currents are diamagnetic, which means that the plasma pressure itself supports the current. So current drive is one of our biggest issues. That's how to keep the magnetic field going after you start it up. And the amount of flux you need is key. Obviously, achieving a high flux, you have to achieve a high amount of flux in the thing in order to actually compress it down and get it hot and make it fuse. We have had a fair amount of difficulty technologically getting a high amount of flux in our devices so far without using very high voltages and powers. Like I said earlier, this is an ideal geometry for space propulsion, and we at one point had a NASA contract to study sustainment of an FRC for space propulsion, and this would be a sort of a idealized FRC rocket, if you will, where you have your plasma exhaust coming out here, hurtling you through space, and on the other side you use direct energy conversion to power your spacecraft. And then once you land, you can put this thing down and use both ends for generating power if you need to. And also in space, the helium-3 fuel may not be so hard to come by. So I want to talk a little bit about the program we have at University of Washington. Right now we're looking at developing a technologically simpler formation method so that we can sustain our FRCs for a steady state. We're conducting basic studies of equilibrium and stability, and one of our big problems is fuel recycling. We have hydrogen comes off the walls of your device while your plasma is running, and it's cold. You have to burn a lot of energy in ionizing it and getting it into the plasma. So one of the things we're working on is reducing the amount of hydrogen we get off our walls that cools our device down. And our main focus is on rotating magnetic field current drive, which is similar. I'll show you the next slide, I believe. It's similar to an induction motor in how we actually start our plasma. And in the next few years, we're going to be working on recycling and impurity control, meaning in a high vacuum system like ours, a few percent of oxygen or carbon or something like that is not hydrogen can kill you. It radiates an enormous amount of energy away. On our last device, the oxygen alone that was coming off our walls was radiating all of the power that we put into our plasma away. So we weren't able to get it hot at all. But we're making great progress. Here's a picture of our device. It's our main plasma chamber here. We have a chamber down here where we are able to make FRCs with a high voltage method that are very hot, very dense, and that's would be used possibly in the future to fuel a steady state type of FRC that's sitting in this chamber. Here's another shot of our central chamber. These are our solenoidal field coils here.
And those are circular?
Yes.
So you're using a linear magnetic field?
Linear magnetic field. So the magnetic field all points this way, down the device this way. Here, difficult to see, but we have our rotating magnetic field coils. I'll get into those a little bit later, but these are what generates the current that makes our FRC. And for anybody who comes to the tour afterwards, you can look at that up close and personal. Just another shot of the machine here. So the basics of RMF current driver, which we do, are very simple. You have a plasma in a theta pinch field. You turn on a magnetic field that is in a Helmholtz pair, so it creates a field that just rotates around this way with the 90 degrees to the solenoid field, and it drags the electrons with it. And it's similar to how an induction motor works in that it drags the electrons create a current. This current then creates a magnetic field, and the magnetic field then forms the shape of the football, basically. The beauty of this is that there's no other magnetic fields that are inherent to this thing that can cause, in a tokamak, the main magnetic field. Also, there's another toroidal field here, and that's takes an enormous amount of the energy of the device to sustain. So this is what allows us, this simple field configuration allows us to stay linear. And also, if you'll recall, with the theta pinch, plasma would just run out the end. Well, in this case, the plasma is all confined because the magnetic fields are connected in on themselves inside the toroid. One of the main accomplishments that we've done at our facility on our new device is we've drastically cleaned up our vacuum system. One of the problems we had in our old system was we had rubber O-rings and dirty vacuum walls, basically. We went to great length to develop a system that had no or a minimum amount of rubber or non-steel and copper gaskets vacuum system. And we took great lengths to make the thing very clean. We built a clean room when we put this thing together. And we've also employed heating blankets on our walls to make sure that you can drive things like water and carbon dioxide and other impurities off and make the thing as clean as possible. And it's paid dividends in our operation already. Our first shots, we were able to produce 200 electron volts of temperature. Keep in mind, we need about 10,000 in order to reasonably do fusion. But compared to what we had before, which was about 20 electron volts, this is an enormous improvement. So we're pretty happy so far. Is that good? show some data on sort of our, this is, in blue is our previous device. And this is fired at exactly the same rotating magnetic field and solenoid field conditions. You can see the factor of 10 improvement in temperature. Our magnetic field we were able to achieve inside the FRC was 50% higher. The same driving fields and lower density. We would like to have a higher density, obviously. That's a technological limitation that can't really get into just due to the complexity of it. One thing we have been able to show is that we're essentially able to operate at steady state, which has never been possible with an FRC up to this date. This chart shows that our RMF field, as long as our RMF field is on, our configuration stays intact. So we're able to drive current as long as we're able to keep our RMF field on. The droop here is just due to the fact that our RMF field is generated by capacitor banks, and capacitor banks run out of energy eventually. But if we could come up with a solid state system, we could run this thing essentially forever. And that's another enormous breakthrough that we've had. So we're in the process of proposing a new facility at the UW, hopefully. It'll be a much larger device, and it will be sort of a proof of principle device to show that this can take the next step up and try to become a reactor. It'll be much larger. Our device now is about 1 meter across. The new one will be about 2.5 to 3 meters. All of our antennas and everything else will be inside the vacuum vessel, so we won't have some of the issues we have with quartz. Right now, our main vacuum vessel is actually made out of quartz. We have to have an insulator in order to get magnetic fields through. So we want to go to an all-metal chamber, and in order to do that, we have to put everything inside. It's one problem with metal is magnetic fields don't really like to go through it. It's resistant, non-resistant, I should say. And we also want to add neutral beams. I don't know if you know what anybody knows what a neutral beam is, but it's one of the principal ways that Tokamak's actually used to drive current. And basically what it is it's a particle accelerator where you get a hydrogen or a deuterium atom moving at 10 kilovolts of energy or 100 kilovolts of energy, or however big your beam you want to make. And at the end you have a grid that recaptures an electron, and so you've got, at that point, a very high energy deuterium atom that's electrically neutral that you can fire into your machine. And so that's a way of injecting high energy particles into your device. And then with charge exchange, you'll end up getting, you capture these things and you can drive current with them that way too. Tokamaks typically shoot them in, and then they're able to sustain their toroidal current, which is the main current that runs a tokamak with a neutral beam. And we want to do the same thing. But to this date, there have been no FRCs that have had the plasma parameters that were capable of using a neutral beam, and we are very close to that right now. So, in summary, fusion will be necessary if we want to power the energy needs of the world for more than the next few hundred years. Can bridge the gap with fission, but as long as the human race plans to be around more than 10,000 years or so, it's going to need to be fission or fusion. Tokamak test reactor is being built. That should show the feasibility of a fusion reactor as a commercial energy source. That ought to be done with construction in about, I think, 2012, I believe, and they're supposed to begin operation sometime around then. At the University of Washington, however, we're researching a concept that's much more engineeringly simple, and we think offers significant advantages over a tokamak should the physics pan out. questions?
So you've got some energy out directly from the helium atoms, charged helium atoms
Yes.
coming out, but most of the reactions also produce the hot neutrons.
That's correct.
Would your whole chamber be hot from that, or how do you get that energy out?
And could you repeat the question?
Yeah, so he said, asked about the hot neutrons. So some of the reaction comes out, the deuterium-tritium reaction comes out in helium alpha particles, and some comes out in neutrons. Typically in a fusion reactor, what you want to get is something called ignition, where your helium actually gives up its energy to deuterium atoms and tritium atoms and heats them that way. So you can turn off, in some sense, your external heating supply devices and get your fusion reaction products to heat your plasma. The neutrons would then be captured. What people are talking about now is a liquid lithium wall that would surround your entire device, and the neutrons would hit the lithium, and obviously that would heat that up, and then they run a steam cycle. Using so you'd have a liquid lithium wall, you'd probably have a water bath on the outside of that as well.
That's going to be outside of your containment field?
Would have to be outside the containment, or the vacuum vessel, but not necessarily outside the magnets.
Right.
Right. It's a metal, but.
Not a physics question, but we've had a couple of alternative to tokamak fusion folks come in and talk to us in the past year or so, and they seem to get a lot of pushback from the established fusion field on doing something other than tokamak, and I was wondering if you've experienced the same kinds of issues.
Yes. When I first started grad school back in, it's like 90.
You might want to repeat.
Oh yeah, he asked about whether or not we were getting sort of pushback from the tokamak community, being an alternate concept to the tokamak, and the short answer is yes. Tokamaks have a really they have a large political inertia. There's a lot. They have big labs. Princeton is one of the biggest fusion labs in the country, and it has a lot of people who have a lot of political connection, and they're a tokamak lab. However, Princeton is moving sort of away from that now as well. Like I said, in '93, all research that was not related to the tokamak was actually cut. Actually, that was back in about 1990, that all research not related to tokamak was cut. Magnetic confinement anyways. And so we survived by taking our FRC and turning it into a tokamak fueling device. Which, it sounds funny, but the nice thing about being a linear device like that is you can
Shoot stuff out
the end. And that's one of the things that our here, so this source here, this is actually the source that we used for doing that. We can create FRCs in this manner, and it's really actually a beautiful concept, because you just energize the magnets at the back very slightly, and you can push the thing. And it's like squeezing toothpaste out of a tube. You just kind of push on the back of it a little bit, a little bit, a little bit, and just give it a little bit more energy as you go, and you can get these things up to tremendous velocities. So we had a pretty successful program actually showed that we could reasonably fuel a tokamak with an FRC. So that sort of bridged the gap. And then after that, money started to flow a little more freely. And then the last couple of years, there's been a real big focus on ITER. So there's been some fear in the alternate community that ITER is going to soak up all the money. But now we're not in ITER anymore. So who knows?
Right.
About how much money is involved in this kind of research? How much funding do you guys need to be able to do this?
Okay, so he's asking about the amount of funding for all of fusion or just us?
So first all of fusion, and then how much money do you guys need?
All of fusion is, magnetic fusion is somewhere in order of $200 million a year, I believe, including
Is that the United States
that's
only?
the United States only. Yeah. ITER is something like $1 billion a year, but that's spread out over several countries, and not everybody's really pumping all that money in right now. Our budget, I think, is somewhere in order of about 1.5, $1.8 million a year, so it's pretty small.
Who provides this budget? Is this,
Ours is the Department of Energy. Yeah, the Department of Energy does most of the research. There's a company down in LA now that's doing some private research actually on FRCs. This is venture capital, and they're running at about $20 million a year, but they're really pushing hard to try to get something started. Our next facility that we're proposing to build would probably operate in around the $5 million a year range.
How do you manage your construction in a university environment?
So he asked, how do we manage our construction in a university environment? Very slowly. We did our whole upgrade with no additional funds. So we had some overhead return and some things like, we had some sort of a slush fund that over the years that we had built up that we were able to buy out a lot of the equipment with. But building stuff in universities is difficult, especially when you have relatively low funding levels like we do.
Are you doing the manufacturing?
What's that?
Are you doing the manufacturing with parts you're able to obtain?
We don't do the manufacturing. Well, it depends on what it is. Most of the stuff is through commercial companies. We have a lot of parts from other labs. Particularly Los Alamos has provided a bit of our equipment. We were able to buy some equipment from Princeton, some diagnostic equipment from Princeton, but for the most part, our vacuum chamber is all bid out to private companies. MDC Vacuum, Kurt Lusker Vacuum, a couple of places like that. They're sort of the big vacuum companies. Most everything was done. We don't have the facilities to do much more than some machining of parts, so it's a slow process when you don't have a lot of budget to do it. I think it took us about almost 3 years to do our upgrade. Something if we'd had the budget and the manpower, we probably could have done in 6 months.
So we had a talk from Bussard,
Yes.
actually talked in California, and it sounded really exciting, but we only heard his point of view. Have you evaluated that technology?
So he asked about Dr. Bussard's electrostatic trap, whether or not I've evaluated that. I've seen his talk. I've actually seen him talk several times, and I know several people that work on that stuff. I don't really understand it well enough to make a evaluation on it, other than there's always a gotcha. It seems very simple, and like any concept, the people who believe in it really believe in it. And if it worked, it would be phenomenal, because it really is a very simple technique. But you kind of got to wonder, why hasn't it been able to move to the next step? And a lot of it may be funding. I don't know. I mean, it's not something that's been funded at any kind of level. There's some guys George Miley's been working on this for years. There's some people down at Los Alamos that have been working on this for a while. But I really don't know. I don't really know the details of it well enough to make a judgment, other than to say there's always a gotcha somewhere. So, but I'm pretty much up for anything that works. If they can make fusion work with that, that would be fantastic. And that is actually probably one of the best, if it worked, would be one of the simplest devices you can make, and it burns the best fuel. So. Sure.
On that, what does it take for you to run 4 on 11 proton or one of those other no neutron outputs?
For us, boron-11 is probably, at least in my grandkids' lifetime, not technologically feasible. D-helium-3, I think, is doable. It's only a few Tesla field for an FRC to be able to do D-helium-3. The problem, obviously, is we haven't overcome the physics barriers, and even to get to the point where we can do DT. So, you have to take a step at a time. It's really, the FRC really is the only magnetic concept that can burn helium-3 and has a potential to burn boron-11. There are other FRC concepts out there. Another guy, one of our colleagues at the university, works on sort of using the acceleration technique. He has two of these devices that he aims at each other, and he slams two FRCs into each other from opposite ends and then crushes them down. He also has a device where he, at least in that he's trying to build, where he would shoot one of these things out and accelerate it into an ever shrinking tapering coil, and then would basically take the kinetic energy, which is really easy to put into these things, into thermal energy as it slows down and compresses into this coil, and you can get a burn that way. Those are inherently pulsed machines, so if you're happy with pulsed devices, then that would certainly be a way to go. And actually, I kind of like those. I actually kind of like that concept. I worked on some of that with him as a grad student. It's very interesting indeed. But steady state is very nice if you can get that.
So you've done this upgrade, and I'm just wondering, what's your current challenge to be working on? What's next?
Well, our current challenge now is we have an RMF field that is. I'm trying to see how to explain this best. The coils generate a field that is just moves in one direction, and if you look at it for a few moments, you'll realize that you have a magnetic field that's closed and another magnetic field going through it that's open, and you add them together, you get a magnetic field that's open, which is the whole idea of our concept is that it's all a closed magnetic geometry, so that you don't have electrons and photons running out and hitting walls and that sort of thing. So there is a way of running the coils where you run them sort of, you have two sets that run opposite directions that actually keep those field lines closed. So right now we're working on trying to get that working. That's been a major challenge, and also we're working on different frequencies of trying to speed up our RMF. We don't have a lot of power is the problem. So the higher frequency we go in our RMF, the lower amount of power we have to put into the device. And ideally, you'd want to go at a much higher frequency than what we're running at now.
How do you guys go about building devices like this? For example, you mentioned that you have a problem to solve right now, but how do you actually go about solving the problem? How do you start tinkering with these devices? You've got wires, and so how do you know that you're moving into the right direction?
Oh, well, okay, so he's asking how we know we're moving in the right direction, what knobs do we turn in order to do this? Well, we have a set of basically magnetic field coils is our main diagnostic. So on the outside of the chamber, we have loops of wire that measure magnetic fields. If you put those in a particular configuration, you can actually measure the size and shape of the FRC. It's a unique property of the FRC. We also have an interferometer system which measures the density. We have various diagnostics, spectrometers, a lot of spectrometers, monochrometers that measure spectral lines of carbon and oxygen to see how much impurity we have. We have a camera that can actually use a spectrometer essentially to measure the velocities of hydrogen at various points inside the device. So we have a fairly wide range of diagnostics. There's one more diagnostic that we want to put on the machine that directly measures electron temperature, which is would be a big benefit to us. We don't have that on yet. It's another one of those $100,000 diagnostics that we're slowly building up the money for.
So who's building all these parts?
Well, assembly was all done in-house, so our technicians and our grad students and our scientists. We go out and turn wrenches, put the thing together. Most of the actual parts are built by various companies, standard government low bidder.
How do you use computers to work on this device? Do you do any kind of simulation or
We have,
analysis, all this kind of stuff?
how do we use computers? We have actually a group on campus that does nothing but simulation work. That's a relatively new group over there. Does nothing but simulation work on FRC's Spiramax, which is another alternate Tokamak concept. And then all of our diagnostics, the signals from them are digitized and go into a screen room and then out, and we use our computers to run the machine, run the diagnostics, monitor everything. But I think probably your question is more, we have a simulation theory group that uses computers, and they use the supercomputers down at more over there.
Do you expect, like, I guess leading up to fission, I guess there was sort of the Manhattan Project, and there was sort of this expectation that there's going to be a eureka moment where they figure out what causes it to work. Like, do you guys think there's a consensus that maybe the ITER is at eureka, or are you close to eureka, where things sort of get simpler at a certain point, or you start now working things backwards, reverse engineering and simplifying? But I guess fission reactors have gotten simpler over the years since they were first developed. Like computers have gotten simpler.
Sure.
To a certain extent.
Yeah. As far as our concept goes,
Chips.
I don't know. We're quite at the point. We've made a sort of with this current drive method, sort of a eureka moment, if you will, on that. As far as the Tokamak goes, I don't know that it can get much simpler. They're actually moving more towards the larger and larger, and that's what the physics demands, is to get bigger and bigger. Our concept itself, if it worked, would be that very thing. It would drastically reduce the complexity and the size of a reactor compared to a Tokamak. But I think the Tokamak itself probably will work. Physics-wise, I don't see any reason why, when they turn a heater on, it's not going to just work. It may produce power at $2 a kilowatt hour, but instead of 3 cents, but it's going to work.
I'm asking again the kind of a related question to the money problem.
Mm-hmm.
So, do you think that money can solve this problem faster, or if you throw more money at this problem, like 10 billion or 100 billion, would that be faster or not?
Okay, so he's asking if throwing some money at this problem would solve it. That's sort of a bone of contention that scientists my age have had with scientists that are older. Right now in the fusion community, there's sort of a break. There's scientists that have been there a long time and they're about to retire, and then there's 30-ish-year-old scientists. There's not a lot of people in between. Basically, yes. And part of that's because funding has been so bad, nobody stays in the industry until recently. The old guys, I call them old guys, have had this 20-year plan, and it includes ITER, and you build this big machine, and you push it, and you go slowly, and then in 35 years you build another reactor that actually might produce some electricity to sell. There's a fair group of younger scientists who would really like to have an Apollo project, which do it in 10 years. Throw some money at it, you know what's going to work, build a bunch of machines to do parallel projects, parallel research, and really try to hammer out what needs to be done, not on one big machine, but on maybe a bunch of small machines. And yes, then here's $20 billion if you need to do it. But a lot of it's political. You know, part of Fusion's problem is early on they sold it as a, hey, we'll have it in 10 years, and it's been 50.
10 years away for 50.
And another problem is that presidents, congressmen don't like things that are longer than their term in office. So when we're trying to sell them a 35-year plan, like, yeah, great, you know, but you know, Kennedy gets credit for the space project because, you know, he launched it. It would have been done in his, you know, probably during his presidential term. But if you sell a 35-year plan to somebody, they're not going to be around. So, you know, well, politically, it doesn't help you much. So, you know, pushing a 10-year plan would certainly, I think, be doable. But there's got to be a political will to do it. And right now, there really is not a political will to do really anything energy-related that's useful.
Is there more interested in bombs, or are they more interested in military uses, or energy is still the higher?
Well, a fair amount of, actually a fair amount, there's a few people who work on fusion or are into bomb research. I mean, at Livermore and Los Alamos, they do the stewardship program, and they bring in scientists and work on behalf on stuff, and they work on the stewardship program. That's certainly something to that. And a lot of the inertial confinement facilities are really geared more towards, well, they really are bomb physics. They say they're not, but they are. But I think the political will isn't there for fusion because it's not. I mean, there's plenty of oil. To be honest, there's a lot of oil. It's easy, it's cheap. There's a lot of people who want to use ethanol, but I don't know. You guys might want to have somebody come talk about ethanol, but I don't see that really worth anything either. You know, people want to use wind and solar, and that's great, but wind and solar isn't base power, so it doesn't run all the time. It's not like a coal plant where you turn it on and it produces a gigawatt forever. So there basically has to be a political will, and you really need a smarter allocation of resources. Natural gas is a really cheap and easy way to build a power plant, but is it necessarily the best fuel for a power plant? It's expensive, and it's really better to heat homes. You know, maybe wind is better if you have a little wind turbine out on your house somewhere up in the mountains or something.
Can this be, you say that there is no political will, and I agree with you, but can that be turned into an economic problem anytime soon, saying that if the prices of energy go up, then it might be that a private company can decide to invest 10 billion or 20 billion so that you build all these machines and make progress?
Yeah, the only way the political will could possibly be there is if energy prices go so high that you have to do it.
I just want to remove the political part out of the equation and just let the investor provide you with capital.
Yeah, well, yes. I mean, certainly an investor is going to do it if they see that there's potential to make a profit there. Right now in fusion, it's far enough off that that's probably not something that there is a company, Trialpha Energy, down in LA that's doing just that. They're pouring $20 million in to try to make essentially an FRC. It's not an FRC reactor. One of the problems is there's not a lot of people. You know, there's 2 labs in the country that work on FRCs that produce people who know anything about them. There's a couple in Japan, but there's not a lot of experts around. Partly because funding has been gone for years. I would love to see a company that would be willing to invest, you know, $20 billion over the next 10 years or so in order to do it. I mean, certainly if you could get it to work, would be once you get the thing working, you'll be able to print money, basically.
So last question, probably.
Okay. While you're doing research, do you have to worry about bad things happening? I mean, in software, you write some code, you try to test it, and then you run it, and all hell breaks loose most of the time. It seems like such a situation here, in the middle of, the industrial district of Redmond, could be kind of hazardous. I mean, you pointed out that, you can have high energy particles, shooting out both ends of this thing. Do you worry? I mean, what?
With our device, no. There really isn't. The worst thing that we've ever done to Redmond was we've ground out. Yeah, in the summer one day we were charging our capacitor banks to full charge. Everybody else had the air conditioners on, and boom! When a substation blew up, and whoops! Soon after that, everyone went home. But since they've upgraded that substation, we have. But that's really the worst thing that we've ever done to Redmond. We have the occasional, high energy arc that blows something up, but that's just
within the confines of the building, right?
Our neighbors are used to hearing bangs and things like that. So, the thing about fusion is it's really, particularly on a device of ours, is really not. We made one neutron, fusion neutron. I mean, we're so cold that you might get one, but probably not even that. So, no, we don't have that problem. The Tokamak does. They do have to be out in an area that's away from the public, and particularly like JET, when they ran at tritium, they have to have a tritium handling facility because tritium is poisonous. So there are some like that for our Tokamak, but for our set of research, the worst thing we're going to happen is an arc. So we're careful with our personnel to make sure no one's around when we're firing out there. But as far as endangering the neighbors, no, nothing other than maybe knocking out the power with them.
Well, thank you very much.